Hello. So we're going to do 6.3 today. We're building on what we learned in 6.2. A lot of it is quite similar, but some of the problems get slightly more complicated. So hopefully this clears up any confusion you may have had after section 6.2. Okay, so we are going to continue solving using separation of variables. So if you remember, that means we're going to collect everything with a y on one side of the equation and everything with an x on the other side. So in this case, we would want to divide both sides by y and by x. I'm not going to show it that way. Let's just write it. Okay, so we're dividing both sides by x and by y. And so on the left, we get 1 over y dy. On the right, we get 1 over x dx. Now we're going to integrate both sides as we've been doing. When we integrate 1 over y, we get natural log of the absolute value of y. Remember, you only need to put the plus c on one side of the equation. Typically, we would do that on the right side, though it wouldn't be wrong to do it the other way. Over here, we're going to get natural log of the absolute value of x, and then we're going to add our c. And then the goal here is to isolate the y. So when we find the general solution, we're going to try to isolate y, and we don't have any initial condition, so we will be left with a c in our equation. So now I'm going to get the y out of the natural log, we can raise both sides to a power with a base of e. We can exponentiate both sides. When we do that, the base e and the natural log will undo each other. And so over on the left, we'll be left with absolute value of y. On the right, it's a little bit different because that plus c is not inside of the natural log. So one big mistake, don't write this down, one big mistake is a lot of students will just say, oh, that's going to be this. But that's not how it works. So it only undoes each other if that plus c isn't there, or if it was inside of the natural log. So that's not what's going on. Instead, what's going on is what we talked about last time. We touched on it briefly. So off to the side, I will show you. If we have e to the natural log of absolute value of x plus c, this is equivalent to e to the natural log of the absolute value of x times e to the power of c, where e to the power of c is some constant. It's a different constant, still a constant. And so if you want to differentiate, you can call this C1, and then you can say, okay, e to the power of C1 is some other constant, we can call it C2. And then the e to the natural log of the absolute value of x can now undo each other. So now this part here just becomes absolute value of x, and then we are multiplying by some other constant, c2. And it's totally fine to just keep calling it c, where c is some arbitrary constant, but if you like to differentiate, you certainly can. So what we're getting is that this right-hand side is c times the absolute value of x. And then we want to drop the absolute value on the y. And technically, when you drop it, you get the plus or minus here. But because this is just some arbitrary c, it is just a constant, it's a placeholder for a constant. And so you don't need to include the plus or minus, versus if we had already found a value of c, then you would want to include the plus or minus. So it's fine to write your answer as c times the absolute value of x. If you want to leave the plus or minus, that's not wrong. Okay, so that's one problem. Let's try another one. Here, again, we have a differential equation that has both an x and a y in it, and so we are going to first separate our variables. So I'm going to get my dy on one side, my dx on my other side. And then I need to move the x squared plus 4 right? I'm going to divide by this x squared plus 4 to move it to the other side. The x is going to stay on the right-hand side, and then we're going to divide both sides by y to get 1 over y over here. Now that we've separated our variables, we can integrate both sides. On the left-hand side, once again, we're going to get natural log of the absolute value of y. On the right-hand side, we've got a slightly more complicated expression this time. And so you've learned lots of strategies now for how to integrate. In this one, a u substitution will work well. So let's do a u substitution. We're going to let u equal x squared plus 4. Du is 2x dx. Dx is du over 2x. So now when I come over and I do my u sub, I'll have this x up here. My denominator is u, and my dx is du over 2x. This is nice, excuse me, because the x's will cancel out. We can bring the 1/2 out front. And then we will be left with integrating 1 over u du. Integral of 1 over u is natural log of the absolute value of u. We're going to put the plus c in there. We're going to resubstitute. The u is x squared plus 4. And once again, we want to rewrite this with the y isolated. So we need to get it out of the natural log. Once again, we will do e to the power of each side. Okay, now this one's a little bit different. Now we still have that plus c, but we also have this 1/2. And so what we can do is we can rewrite this right-hand side as e to the natural log of absolute value of x squared plus 4 to the 1/2 power, right? Where that's like all inside of the log. To the 1/2 power is also, I'm going to write it in another way. To the 1/2 power is the square root of, so we have natural log of the square root of the absolute value of x squared plus 4 plus the c. And just like we talked about oh my gosh, just like we talked about in the last problem, you can bring the c out, but it comes out as a constant multiplier. So we have this. I can also drop the absolute value in the square root because x squared plus 4 is always positive anyway. So if you feel comfortable dropping that, you can. Okay, so what are we left with? On the left-hand side, the e and the natural log undo each other. We're left with absolute value of y equals. Now here, also on the right-hand side, the e and the natural log undo each other. And so what we're getting is c times the square root of x squared plus 4. Okay, and then again, we can drop the absolute value. You can include the plus or minus, but you don't have to because we have an arbitrary constant of c. All right, let's try another one where the wording is slightly different. So in this one, we have find the equation of the curve that passes through the point 0, -2. That is our initial condition. Okay, and has a slope of x plus 1 over y at any point xy. So again, a little different. It doesn't look like we have a differential equation, but a slope is a derivative. So when it has a slope of x plus 1 over y, that is telling us dy dx is equal to x plus 1 over y. Okay, so here we are being given the slope, we are being given the initial condition. We are going to try to find the equation of the line that passes through that point with this slope. So we need to work backwards to find the original equation. This is not to be confused with finding the equation of the tangent line. Here we're trying to find the equation of the actual curve or equation that would have this given slope. Okay, so let's separate our variables. Y dy equals x plus 1 dx. And we will integrate both sides as we've been doing. When we integrate y, we get 1/2 y squared. When we integrate x plus 1, we get 1/2 x squared plus x plus c. Now, like we talked about before, you can find the c now or you can find the c later. I am going to find the c now in this problem. But it might be interesting for you to try finding the c later and seeing how they compare. Sometimes your answers can end up looking different. A strategy to tell if they're the same is graph each of them and see if you get the same graph. Okay, so we're going to use 0, -2 to find c. So let's plug it in. If y is -2 and x is 0, -2 squared is 4, half of 4 is 2, and then over on the right we have 0 plus 0 plus c is just c. So we're getting that c is 2. Okay, so now we're going to plug back in to our general solution here. We have technically found a particular solution, but now we are going to try to isolate the y. So I would multiply both sides by 2. Okay, and now this one's a bit unique. This does happen sometimes. So here, we're going to take the square root of both sides to isolate y. We do need to include the plus or minus here because there's not some arbitrary c being multiplied out front. If there was, then you don't have to, but here we have to put it. And now we are trying to find the equation of the curve. So there is one here that's going to work. So we found two particular solutions. We have the positive square root x squared plus 2x plus 4, and we have the negative square root x squared plus 2x plus 4. And we have to think about which one works with our initial condition. So we look back at the initial condition, which is the 0, -2, and we think about which one of these will have that point on it, the positive or the negative. So if I plug in 0 to x, I want to get out -2. This is like easy to forget, but it is important and it does come up maybe on the test. So maybe make a special note of it. If you are dealing with a plus or minus situation and you are looking at a particular solution, not a general solution, you have to pick the one that makes sense. Okay, here, if we plug in 0 to x, we need to get -2 out. And so the only way to get negative would be if we choose the negative solution. And so our answer is this one. Okay, so that was continuing to practice separation of variables in a few more types of problems, a little more variety than last time. And now we are going to do a few more modeling problems. So we did modeling problems last time. We practiced that. We practiced working with the exponential functions, trying to find a c value and trying to find a k value. We're going to do the same thing here. There's just like a little bit more to it. So first of all is going to be how it's worded. The rate of change of the number of coyotes, N of t, in a population is directly proportional to 650 minus N of t, where t is the time in years. When t is 0, the population is 300. When t is 2, the population has increased to 500. So first, we need to set up the differential equation. It's not given to us. So we're going to use the words like we practiced last time. We're going to try to convert the words into a differential equation. So the rate of change of the number of coyotes, N of t, so that can be represented by dn dt. You can write dn of t, but it's fine to just write dn. Is directly proportional to 650 minus n of t. So that's where we do the k times 650 minus, and again, I'm just going to write n. That's totally fine. Then we're also told when t is 0, the population is 300. So let's write out an ordered pair. And when t is 2, it's increased to 500. So those are the initial conditions that are given. So let's write our differential equation. Our differential equation will be dn dt is equal to k times 650 minus n. Now we want to solve it. So if you recall, last time we talked about if you had like the rate of change of y, maybe I can write it off to the side. If we had the rate of change of y equals ky, we said that the answer or the general solution would be y equals c times e to the kt, and you could get there without doing any work. This is very much related to that, but it's slightly different because it's not just ky, and so there is a shortcut. We're going to work through it the long way so that you see where that shortcut is coming from. If you feel comfortable going straight to the shortcut, you are welcome to do that, but this is good practice with the calculus part anyway. So write a general solution. We're going to separate the variables first. I'm going to divide both sides by 650 minus n. I'm going to leave the k on the right-hand side, and I'll have dt. Now we're going to integrate both sides. Okay, when we integrate the 1 over 650 minus n, I'll do the full u substitution off to the side. So if we have u is 650 minus n, du is going to be negative dn. Wait, yes. Okay. Du will be negative dn. And so when you do the u substitution here, you're going to get 1 over u du, and you can pull that negative out front. So we're going to have negative that. Okay, so that's the u substitution that's going on. I'm going to erase it and just write down what we end up getting here. So we're going to get negative natural log of, because when we integrate 1 over u, we get natural log of u. U is 650 minus n. And you actually get kind of lucky in this case if you forget about the negative, which is like a common mistake to make. If you forget about that negative out front, the problem ends up working itself out because you have to find k and c anyway. So if you forget it, it's not really a biggie. Okay, we get this. We're going to do exactly what we did earlier, but before you exponentiate both sides, you really don't want this negative here, and so I'm going to divide or multiply both sides by -1 first. I can write negative c, but I'm not going to because, again, it's just a constant. Also, k is just a constant. You don't really have to put the negative, and that's why I said it works out if you forget about the negative in front of the natural log because we have these two constants on the other side anyway. So we'll try to be mathematically correct as we show our work here, but it would work out if we were not. Okay, we exponentiate both sides, then we're left with 650 minus n in the absolute value equals, hopefully now you're feeling comfortable with, I can bring this c out front, and then I'd have e to the negative kt. Now I'm going to drop the absolute value, and I don't have to put the plus or minus because c is just a constant. I'm going to add n to both sides, and I'm going to subtract the c times e to the negative kt. Okay, so maybe you can see the connection here. I will highlight it to point it out to you. This was our differential equation versus the differential equation we were working with last time, which was just dy dt equals ky. Here we have dn dt equals k, and then 650 minus n, so it's not just an n in there. And so our solution is, instead of y equals c times e to the kt, here we got 650 minus n equals c times e to the kt. And the k does have a negative, but like I said, if the negative wasn't there, it would still work. So you could go straight to this, but only if you fully understand the process that gets you there. If you don't, then you need to really keep practicing that. Okay, but if you feel comfortable and it feels repetitive, like every time you do one of these, you're doing the same thing over and over, you can just skip to the solution. All right, so we have our particular, no, we don't. We have our general solution. It's not a particular solution yet because we don't know our c, we don't know our k. So because we have two missing constants, we have two initial conditions. We're going to plug in the 0, 300. Be careful here, c is not 300. So a lot of times people think like when time is 0 that this value is going to be c. No, not always. That's only if it looks like c times e to the kt. This one's a little different because it's 650 minus that. So just be careful. Okay, use 0, 300. So we're going to plug in. I'm going to use this equation here. I'm going to have 650 minus c times e to the k times 0 equals 300. So I'm plugging in 300 to n, 0 to time. E to the 0 power is just 1. And so we have 650 minus c is 300, and so c is 350. Now I'm going to write my equation again. N equals 650 minus, okay, now I'm going to plug in my c, 350 e to the negative kt. Okay, so all I did there was I replaced my c with the value that I found for it. Now we can use the next initial condition, which is the, 2, 500. So now we're going to use 2, 500 to find k. From here, we really did this last time. So I would encourage you to just like pause the video, try to do it yourself, and then fast forward and see if you get the same thing that I get. Okay, I'm going to subtract the 650 from both sides. Negative 150 equals negative 350 e to the negative kt. I'll divide both sides by negative 350. And now I'm just going to make those positive, maybe simplify it a little bit. 15 over 35, you can of course simplify that more, equals e to the negative kt. Then we natural log both sides, and that natural log would bring out, oh my gosh, oopsies, hold on. In all of these, my t should be a 2, right? Because we're plugging in at time 2, we get 500, so we have a 2, a 2, a 2. Okay, so here now I have negative 2k. divide by the -2. That's my exact value of k. And then we can write out our solution. I'm running out of space. N equals 650 minus 350 e to the, okay, now be careful here. Look, you guys, here we're getting that k is a negative. Okay, we're getting that k is a negative. But in our general solution, this was a negative k. And so actually, we have a positive value here. We have a positive 1/2 natural log of 15/35. If we are dealing with exponential growth, then the value that you have here should be positive. So that's a good thing to check for. So this is our particular solution. And then to answer the question, which I'm not going to do right now because I don't have my calculator with me, is now you'd plug in t is 3, right? So it's asking to find the population when t is 3, plug in t is 3, get it in your calculator, and you'll have your answer. Okay. So really the only new part is the part B. Part C is what we were doing last time. One more question. We're gonna solve a crime here. So, well, we're not gonna solve it. We're gonna help solve it. This problem we're gonna do is based on Newton's law of cooling. Newton's law of cooling states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So I'm going to try to write this out in a way that makes maybe the most sense. Let's let y equal the temperature of the object. So the rate of change in the temperature of the object, so that's going to be dy dt. The rate of change in the temperature of an object. The object's temperature is y, so that's dy dt, equals, it's directly proportional to, so there's the k, and then the difference between the object's temperature and the temperature of the surrounding medium. So the object's temperature is y, and then temperature of the surrounding medium, I'm just going to write surrounding temp. Okay, that is Newton's law of cooling, which is pretty cool. So let's go to try. At noon, a corpse was found in a room with a constant temperature of 60 degrees Fahrenheit. That wording is not great. The 60 degrees Fahrenheit is the room temperature. This is the room. And at noon, the body was 80 degrees Fahrenheit. At 3 p.m., the body had cooled to 72 degrees Fahrenheit. Find the time of death. All right, maybe it was a natural death. Maybe it's not a crime, but it's a little more fun if it's a crime. Okay, so here we go. We can start by writing our differential equation. So step 1, set up your differential equation. dy dt equals k times y minus the surrounding, so y is the temperature of the body, okay? We're going to try to find the time of death, so we're going to be solving for a time. And then the room's temperature is 60 degrees, so it's going to be y minus 60, y minus the surrounding temperature. Okay, now we're going to solve this first, this differential equation. So separate the variables, we get 1 over y minus 60 equals k, dy equals k dt. We're going to integrate both sides. If you understood what I was saying on the previous problem, you can fast forward this part. If you feel like you need to see another example, like worked through, then stay with me here. Okay, so here we would get, when you integrate 1 over y minus 60, if you're u, right, integral of 1 over u is natural log of the absolute value of u. So this is going to be natural log of the absolute value of y minus 60 equals k. K is a constant. We're integrating with respect to t, so it's going to be kt plus c. Now we don't have that negative in front of the natural log, so we don't need to worry about that. We are going to exponentiate both sides. By doing that, we've lost the natural log there. And the e to the kt plus c, as I've showed a few times already in this lesson and last time, the c can come out front as a constant multiplier. It's a different c, but it's still a c, a constant. Then you can lose the absolute value. You don't have to write the plus or minus. You can, but honestly, it just makes it look more complicated. And then finally, add the 60 to the other side. All right, we've done it. Now we are going to need to plug some stuff in to help us find C as well as K. Okay, so what information is given? We're given that at noon, the body was 80 degrees Fahrenheit. So we're going to consider noon to be time 0. So don't plug in like 12 for noon. We're going to consider it to be time 0. And then at 3 p.m., the body had cooled to 72 degrees Fahrenheit. You could do this in hours. Like you could put 3 and then 72. But then if it's in hours, you're finding the time of death. You're going to have to like convert it to a time. You're going to maybe convert it to minutes. So I'm going to set this up with minutes. So 3 hours later would be 180 minutes later. Okay, so not wrong to do it with hours, maybe a little easier to do it with minutes. Okay, so now step 2, we're going to use 0, 80 to find C. So I'm going to plug in 0, 80. That's just 1. The e to the 0 power is 1, and so C is 20. So my new equation is y equals 20 e to the kt plus 60. Now I'm going to use the next initial condition that I have, which is 180, 72. We're going to use that to find k. Okay, so we're going to plug this in. So we get 72 equals 20 e to the k times 72 plus 60. Start to solve. Subtract 60 from both sides. We get 12 equals 20 e to the 72k. Divide both sides by 20. Wait, what am I doing? Ah! This is not 72. This is 180. Okay, divide both sides by 20. We get 12 over 20 equals e to the 180k. And then little natural log action. And so k is natural log of 12 over 20, or simplify it, divided by 180. Okay, now you're not going to start writing that as a rounded decimal. You're either going to write it exact, you could type it in your calculator, store it, but do not round and use your rounded answer later. You will overround. Okay, so that's my k. Since I've clearly defined my k, I could like box it, and now when I go to my next step, which is going to be up here, I could say y equals 60, or let me write it in another order. Y equals 20 e. So I'm going to write it out. 12 over 20 over 180. I like to write it out one time just to show that I know that this is the equation that I'm working with. But you could, since you have clearly defined K, if you want to just keep writing KT, know that you have it stored in your calculator, that would be fine as well. Okay, so now how are we going to find the time of death? That's the question. Find the time of death. So here we're solving for a time rather than plugging in a time. So you got to think about at the time of death, what was the temperature of the body? Because that's what we're going to need to plug in. So we're going to plug in an ordinary body temperature. Do you know it? What's the temperature of the human body? Ideally, 98.6. So I'm going to do this. If you want to, you can just write a K here, or you could just go like this. Do it in a way that works for you. If you were doing something like this on the actual AP exam, it would be worth it to write it out like every time, even though it's kind of annoying. I would just do that. Subtract 60 from both sides. Okay, now you're just solving a log equation, so, or not really, it's an exponential equation using logs. Divide by 20. Divided by the K, and remember this I have stored, I don't actually have my calculator, but let's pretend I stored in calculator. Okay, so then I type that into my calculator and I have an answer from last year, so hopefully it's right. If it's not, well, we can circle back next class, but I believe you're gonna get negative 232. Probably with some decimals, but I don't have that written down. So that's representing the time of death. Negative 232. Remember, we're using minutes, so that's kind of weird, but that means, remember, times zero was noon. So this means the fact that it's negative means 232 minutes before noon, and so you can figure out the time if you'd like to. I'll leave that part up to you. All right, there's your homework. These types of problems, study them. It's very repetitive, so hopefully you can get the hang of it. And then you'll have some practice in your review packet next class. I'll see you soon. Bye.